Hello there, my name is Monique and I'm here to talk about how this simple toy, or as simple as it looks, can be used to explain the group theory. No, I won't be teaching you how to use the group theory to solve your Rubik's Cube since that will be in another video. But for today, I'm going to be teaching you the relation of the group theory, symmetries, and the famous cube of Rubik to prep you for the day where you finally get to solve your very own Rubik's Cube. But first and foremost, let's try to understand what group theory really is. Group theory is basically a study of groups under abstract algebra. These groups are sets equipped with an operation like multiplication, addition, or composition that satisfies four actions, or in simpler words, basic properties, which are used to analyze the sequence of permutations that will result in a solution. These actions are closure, associativity, identity, and inverse, which we will be explaining a little bit later. The concept of groups are vital to abstract algebra because their basic structure can be found in many mathematical phenomena that studies and manipulates abstract concepts involving symmetry. Since group theory is a study of symmetry that arises naturally in physics and nature, it has applications particularly in atomic and molecular spectroscopy, chemistry, which focuses on molecular orbital theory, computer science when it comes to research in robotics, computer vision, and medical image analysis, and, of course, mathematics for puzzles like this Rubik's Cube that I am holding. A symmetry is a transformation that preserves distance and object. Well, there are two types, reflectional symmetry and rotational symmetry. Reflectional symmetry means that there is only symmetry on only one axis. And this Rubik's Cube observes the other type, the rotational symmetry. This means that the symmetries of this cube satisfies all four axes, horizontal, vertical, and the diagonal axis. Now, if you place the cube between your thumb and one of your fingers to the two diametrically opposite corners of the cube and give it a 120-degree turn, you can see that after 3 turns, you go back to the first face of the cube. This just simply means that the cube has a threefold symmetry. Well, yes, I know you have been watching this video to understand how this thing does work. So, I'll be introducing to you to this guy over here. The Rubik's Cube, a 3D combination puzzle invented in 1974 by Erno Rubik, who is The Rubik's Cube, a 3D combination puzzle invented in 1974 by Erno Rubik, who is a Hungarian architecture professor that created this magic cube and hopes to teach his students about three-dimensional spaces. It is a popular mechanical puzzle that trains your brain, resulting to improved patience, concentration, memory, reflexes, and even problem-solving abilities. So, what's so special about this cube, anyways? As you can see, the Rubik's Cube is composed of 27 small cubes which are called as cubies. Cute, right? So basically, there's 3, 6, 9, and 9, 18, and 27. So, total of 27 cubies. However, only the 26 cubies are visible since the last cubie is basically non-existent if you ever try to take a cube apart. So, instead of the 27th cubie, the center shaft frame is inside to allow the movement of the pieces. The cubies you see here on the corner are called corner cubies, and each of the 8 corner cubies have 3 visible faces. For example, this corner cubie has 3 faces, the white, the red, and the blue. On the other hand, here is a cubie with 3 faces of yellow, orange, and blue. For the 12 cubies that only have 2 faces, like you see here, this one, this one, this one, this one, this one, as well as this one, are called edge cubies since they only have 2 faces. And lastly, the cubies with only 1 visible face are called the center cubies. And as you can see, there are a total of 6 cubies. In my case, I have color white, green, yellow, orange, blue, and red. So, only 1 face for these center cubies. Now that we have identified each cubes, these set of cubes are actually grouped together to show 6 different faces. If you focus on the plane of the cube, You could observe that just like the center cubies, the Rubik's Cube also has 6 faces overall. According to David Singh Master, we call them the right, left, up, down, front, and did you know that all of these elements can be arranged to an approximate of 4320520027448985600 or 43 quintillion permutations. So how did it become such a large number? Let's consider the corner cubies and the edge cubies. There are 8 corner cubies that can be permuted in 8 factorial ways. Furthermore, each permutation can be arranged in 3 orientations, allowing 3 raised to 8 possibilities for each permutation of the corner pieces. Therefore, the number of possible arrangements for the 8 corner pieces is 8 factorial times 3 raised to 8. On the other hand, there are 12 edge pieces which can be arranged in 12 factorial ways. Each edge piece has 2 possible orientations, so each permutation of the edge pieces has 2 raised to 12 arrangements. Therefore, the number of possible arrangements for the 8 corner pieces is 12 factorial times 2 raised to 12. Now, multiplying them all together, we divide it by 12, which represents the 3 sets of impossible states that cannot be accessed by twisting the Rubik's Cube. With that, we get 4.32 times 10 raised to 19 or 43 quintillion. But don't fret, since in order for you to solve and better understand the Rubik's Cube, you could find its symmetry. To do that, we must first understand the different properties of symmetries, which can also be defined in the set group actions. Let's set dot to be an operation like addition, multiplication, or composition, and G to be a group. First is closure. If X and Y are 2 elements in a group, G, then X dot Y is also an element of G. This means that the composition of symmetries is a symmetry. There is a predefined list of actions that can never change the moves that can be performed on a Rubik's Cube. In simpler terms, the Rubik's Cube would always have a total of 6 different colors representing the 6 sides of the cube, no matter how much I rotate the sides. And the top and the bottom faces of the cube are still the same. Second is associativity. Composition of symmetries is associative. If X, Y, and Z are in group G, then X dot open parenthesis Y dot Z close parenthesis is equal to open parenthesis X dot Y close parenthesis dot Z. You could put the parenthesis wherever you want in the group operation and it would still be equivalent to the same operation but with parentheses in a different place. In simple terms, if you pay attention to this white rows over here and I turn this row 2 times to the right and 3 times to the left, you could see that the row turned into red. Now back to the first order. Let's see. If we changed it and rotate it 3 times to the left and 2 times to the right, it would basically still yield the same result. Third, identity, wherein not doing anything is a symmetry. For any element X in G, there exists an identity element in the set that keeps the set unchanged. Basically, if you add 0 to any number, the value of the number does not increase or decrease. It just stays the same. So let's say if I move these 2 sides and don't turn anything or do any rotation on it, the cube stays in the same position as it is until I move it again. Now to the last axiom, inverse,
where we can undo symmetries.
My favorite. For every X in G, there exists some Y in G, such that X dot Y is equal to Y dot X. If I turn the Rubik's Cube to this particular series of moves, I can reverse it by doing the inverse of the series I just created. And it's back to its initial order. And that's a simple introduction and the basics to group theory. Solving the Rubik's Cube randomly, given that it has 43 quintillion permutations, would take forever. And impossible. However, applying the concept of group theory to the problem to produce a solution could help you solve your very own Rubik's Cube instead of just going to the net and searching up sites to generate solution for your group problem. And that's it! Good luck on solving your very first own Rubik's Cube. Well, I tried to solve my own. Bye!